Yeah, hello everyone. Thank you for the nice introduction and the opportunity to speak in the seminar. We present our paper Quantum Annealing with Learned Couplings, which was recently accepted at ICLR. And this is joint work between the University of Siegen and the Max Planck Institute for Informatics. So in general, what we are interested in is solving combinatorial optimization problems that arise in computer vision with quantum annealing. Here on this first slide, there's some picture of some quantum annealer from this DWEF company. And I will start with a short slide about adiabatic quantum computing. So as you all know, in adiabatic quantum computing, you usually have a model with some continuously changing Hamiltonian. And this could look, for example, like this, where we have a linear combination between an initial Hamiltonian with an easy to prepare ground state and a final Hamiltonian with some interesting ground state. And then this adiabatic theorem roughly states that if tau is sufficiently big, an estimate could depend on the spectral gap. And if we start in the ground state of H initial, then we end up in the ground state of H final. Okay, so in this quantum annealing as implemented in these DWEF machines, you now get some QUBO solver. So you solve quadratic, unconstrained binary optimization problems. And so from an algorithmic perspective, you get some stochastic algorithm comparable to simulated annealing as you get many samples. But it could be advantages for energy landscapes with high and narrow spikes. So this is maybe the picture you have in mind. So you search this energy landscapes more efficiently with this quantum annealing. And then there has been major progress in the experimental realizations of such quantum annealers. So this DWEF 2000Q had 2048 qubits, while this DWEF Advantage has 5000 qubits. So for a specific certain sparse matrix A that corresponds to the hardware graph, this number M here is already the number of qubits, but if this matrix A would be dense, then of course this M would have to build chains and this M would be smaller. Okay, but what do we now did in this work is we wanted to build a neural network that learns this matrix A here. And what is the motivation for this? So previously, if you had some computer vision problem or some combinatorial optimization problem, you would graph this matrix A per hand. And then you would have to develop one algorithm per problem setting. And if you apply deep learning to this problem, then you could have a method where you only need training data and then you get your A matrices. Okay, another motivation could be the following. In general, one often encounters such equality constraints, Cx equals B. And the usually straightforward way to implement them would be with some penalty term. And then you would have to fine tune this penalty parameter. And this could also be a little bit difficult. So if this penalty parameter is chosen too small, then you wouldn't have the constraints anymore. And if it is too big, you could also run into problems with some precision. So these couplings in this DWEF machines, they of course have some errors, and this would lead de facto to some fixed precision. Okay, another motivation of our work could be the following. Consider this QUBO problems where we only have the diagonal entries. Then, yeah, in this case, you could directly solve this problem if you look at the signs of the diagonal entries. And so in some way, having a neural network built before this A matrix would be, if you also have non-diagonal entries, you would have some generalization of this direct prediction of a neural network, I would say.
Yeah, and I will now explain the pipeline and the architecture of our approach. First, we will start with the pipeline. And in the beginning of the pipeline, we have our computer vision problem. here, for example, we want to find out by which angle the two point clouds are rotated. And in the first step, we encode our problem into like a numerical vector P, which we can see in the next step. After this, we're using a neural network to regress our QUBO matrix A, which can be seen there. Then in the next steps, we set up our QUBO, initialize the quantum annealer, and anneal our solution. Then we have generated our QUBO solution X, and we can use this QUBO solution X in order to compute the loss function of our network, and then use machine learning techniques like backpropagation to update our neural network, and then we can start the whole learning process from the beginning. And what is really important here is that we don't need to compute like any of the derivatives of our neural network inside of the quantum annealer, but with our cleverly chosen loss function, we can basically like compute the loss outside of the quantum annealer, which makes it possible to have this quantum annealer in our approach. Then about the network architecture, we are using a linear layer-based neural network, which is also called like MLP, like multi-layer processor. And how does a linear layer looks like? As an input, we get a vector X, and the linear layer consists of a learned weight matrix W, and the output of this layer is again a vector Y. So we can write a linear layer, as we can see here. Y is just the matrix product of W times X. And then we use an activation function to change like the output of this layer slightly. And we use here in this case a radar activation function, and the radar activation function is 0 if like the entry is like below 0, like negative, and it's like a linear function if the entry is like positive. And important here is like, why do we need this activation function? This activation function is useful in order to incorporate some non-linearities in our linear layer, and that makes us able to like basically approximate any function with our neural network. So we use in our experiments 2 different setups, a small one and a big one. On the left-hand side, we can see the small setup, which is a simple 3-layer neural network with 3 linear layers. And on the last layer, we use the sign activation function instead of a ReLU activation function, because this will enable us to also have like positive and negative coupling weights or like annealing weights. And then on the right hand side, we can see our 5-layer approach that is very similar to our 3-layer approach. The only difference is that we're using like a residual connection between the first and third layer, and this helps us in stabilizing the training and making our network more generalizable on our problem settings. About the loss function, our loss function basically helps us to train the network, and as I said beforehand, we don't need to have any information from the quantum annealer in order to be able to calculate the loss. And how do we do this? The loss function can be split into 3 different parts: our accuracy loss, our uniqueness loss, and our MLP loss. Our accuracy loss, basically, we just define how good our solution is, or it's there to figure out that we also have like the minimizing solution as our minimizing energy. Because when we look at the definition in equation 4, we can see that this loss is like minimized basically when the minimizer of our matrix A is the same as the ground truth solution. And the minimizer is basically the vector which like minimizes the inner product of x times a times x. When we take a derivative of this loss, we can see that in the first and the second term, there's like no a term included, and just in the last term, we have like a term where also like a is included. However, we just take an approximation of this derivative, and we just ignore the last term, because in most settings, this last term is 0, except for the boundary where we like change between one solution to the next solution. But as an approximation, we can just like ignore this term and set it to 0, and we can see in the following experiments that our learning still works. Then our uniqueness loss was like the second part of the loss. The uniqueness loss is also can be set in relation to the spectral gap of our matrix A, because it's very important that like the lowest energy level and the second lowest energy level aren't too close to each other. If they are fairly close to each other, then it's like a high possibility that the quantum annealer will just end up in the second lowest solution instead of the lowest solution, and therefore we won't always get like the perfect solution. And in order to increase the likelihood that we anneal to the ground truth solution or to like the actual minimizer of the matrix, we try to increase the spectral gap between the minimizer of the matrix and the second lowest energy of this matrix. Last but not least, we have also an MLP loss. This is basically just a regularizer for our network. Here we just take the L1 matrix norm or the L1 loss of all of the output of the network features, and this regularizes our training and also increases the sparsity, which also helps us to create a more sparse A, which then also helps us to better embed it onto our quantum annealer.
Okay, one class of problems we had a look at is graph matching. So in graph matching, you have two images and key points in these images, and you want to find a permutation between these key points. So for example, here you want to find a permutation that maps the peak of this bird to the peak of this duck, and yeah, so on. So you can formulate this as some quadratic assignment problem, where you have some quadratic optimization problem and you optimize over vectorized permutations. And the way we did this here was, also the weight matrix we choose was some linear combination between this W Alex, which is essentially a diagonal matrix that consists of the cosine similarity between feature vectors that are obtained with some AlexNet. And then we have also some geometric W matrix. So this contains differences in spatial distances between pixels. So we used some specific data set, the Willow data set, where the differences, the spatial differences between these key points are meaningful, and also the direction of these. Okay, how did we deal with the permutations? So we encoded them in a specific way. So let's consider some permutation table here, and each entry is encoded with log n bits. And yeah, one could also think that you could directly convert the quadratic assignment problem at the beginning in this way with this encoding, but this would in general lead also to higher order terms. This was done, for example, in this publication. Yeah, and we compared our method with three baselines: a diagonal baseline where we set all the off-diagonal elements to 0, some pure baseline that we didn't use a QUBO solver at all and had some direct prediction without the final activation layer, and brute force. There we solved this this input quadratic assignment problem directly by exhaustive search. And these are some results for 4x4 permutations. So we have direct graph 97% accuracy, which we also considered as some upper bound what would be achievable. Then our method got 69%. Then the diagonal baseline got a little bit less with 53, and pure got 90% for this application.
Now about point-state registration and rotation estimation. First, what is point-state registration and rotation estimation? For example, here we can see a 3D scene. We have a 3D point cloud of a bunny, and now we want to find a rotation a translation and a permutation such that those 2 point clouds now align or like completely overlap each other, like we can see here on the right hand side. And the point set registration objective can be basically here formulated in equation 11, basically that if you rotate one point from the 1 point cloud, then translated by translation t, then it should match the point from the other point cloud, and the m just indicates that we found like the right point, like the right permutation between those 2 points. So what about like our 2D setup? In the 2D case, we did a 2D point set registration, and in the 2D case, the rotation is relatively easy because it's clearly defined by just one angle. As we can see here in the figure, when we turn the figure F by some degrees, then the rotation is already uniquely defined. So about our setup is that we need to find the correspondences between the 2 point clouds as they are not known. And we also need to find the right rotation in order to solve our problem. We just need to find like one Euler angle, and the Euler angle is encoded as follows. Like we sample like the space between all possible angles. In this case, it was like between 0 and pi third. And then we like split it into like regular intervals. For example, here the angle 0 would be encoded into like 0, 0, 0. And as we can see then in the table that on the next slide, that our method basically always outperforms the diagonal in the pure baseline. In most cases, besides the first one, but there our method is also fairly close to the pure baseline. We therefore can see that it's like from advantage to learn here like the full QUBO and not directly predict the angle between those 2 point clouds, and also not just use the diagonal elements of the QUBO. In the 3D case, the rotation estimation, there in the 3D case, the rotation is a bit more complex. Because in the 3D space, we can rotate around 3 axes. We can rotate around the X, Y, and Z axis. When we, for example, when we want to find out the rotation of this airplane, we first need to rotate the space around the X axis, like shown in the first picture, then around the Y axis, shown in the second picture, and then rotate it around the Z axis, shown in the third picture. And this segmentation is also like called like segmentation into the Euler angles. Our network makes use of this segmentation of the 3D rotation because we do it in different network steps. As we can see here, because in figure A, we can see like the rotated A plane. These point clouds are like fully rotated with a 3D rotation. And then we apply 3 different networks, which each just predicts like one rotation. Like we first predict the rotation alpha, and then rotate the shape around angle alpha. Then we predict rotation beta, and then rotate the shape around angle beta. And then finally, we predict rotation gamma, and then also rotate the shape around the angle gamma. And finally, we get the full solution of the approach. Also in this setup, our method is like highly advantageous compared to like the pure and the other baseline, because we are using again the same setup as in the 2D case. However, now the angle encoding is like more complicated because we have like 3 different angles, and the 3 different angles get like encoded individually, and then finally just put together. Like the final solution is basically it's like a 9-bit string, and then the first 3 bits we have the first angle, the second 3 bits we have the second angle, and the last 3 bits we have like the last angle, as we can see down here in the last line. If we would encode alpha, beta, and gamma, we would then receive this string. And here we can see that again our method, similarly to the point set registration setup, basically outperforms the diagonal and the pure baseline. And we can also demonstrate here that our methods is like also like better suited to this problem setup than the just using the diagonal of the couplings or just like predicting the angle directly.
Okay, for the graph matching experiments, we also performed the training directly on this D-Wave machine. And for this, we had to find some good way to embed the problems. So here we have some tiling embedding. So one tile is encoded with one color. And so we could solve many QUBO problems in parallel with this. And here are some results for for our method trained with D-Wave. And we use this on the random graph data set where we just had random uniform sampled the distances of these graphs. And we also applied projection sometimes. So it's not guaranteed that we get as encoding a valid permutation, but one could always project onto the permutations. And yeah, as we see, we got even a little bit better results if we trained this on the D-Wave than with just the simulated annealing solver. But yeah, the explanation, also this is not such a profound reason. The explanation is just, can be just got by looking at the histograms of the individual QUBOs that are solved. So the vector for the second lowest energy was also important for our method. If you remember the losses, in one loss, this vector occurred, and this was a little bit easier to obtain than with this quantum annealing here. Okay, here we also have some picture of the matrices during the training. And again, the errors on the rotation estimation. So we have the errors in degree, which are quite low. So here it was trained with exhaustive search. And for the test data, we looked at exhaustive search, quantum annealing, and simulated annealing. And here we saw that quantum annealing and simulated annealing performed similar, and exhaustive search had a slight edge here. And to sum everything up, so we showed that quantum annealing could be useful for combinatorial problems that arise in computer vision, and one can get the QUBO encodings via a neural network. Yeah, we performed first experiments on the quantum annealer and showed usability for 2 different computer vision problem settings. Yeah, extensions of this work could be to test different network architectures and also look at further computer vision problems. And with this, I thank you for your attention.
Good, thank you very much, Marcel and Maximilian. Very nice. Round of applause from all of us. And I'll open up for questions. I think I saw Viv Kendon had raised her hand briefly. Are you there, Viv?
I'm here, but that was a mouse error trying to record. It's a nice talk, definitely.
Thank you.
Any other questions from members of the audience? Well, maybe I'll ask a question then. So I get, if I've understood correctly, your optimized QUBO encodings, which sort of define this matrix A for a given problem, do not take into account the underlying hardware architecture that you have at your disposal. Have I understood that correctly?
Yes.
So you've assumed a priori that you have a complete graph in your hardware. Is that also correct?
So let me look at the slide with the tilings.
Yeah.
So yeah, of course, these everything that is colored in one color is not a complete graph. But for these experiments where we did the training on the D wave, we just simply ignored the couplings that are not the qubits that are not connected. So it's in principle something between this diagonal baseline and something where you would have full QUBOs.
But presumably you could recode it reasonably easily, I think, so that you're only adjusting the parameters of your matrix A in a way which can be directly embedded onto the hardware. Is that correct?
In which way adjusted?
So I guess
I guess
in your hardware connectivity, many of the off-diagonal, if not most of the off-diagonal terms are zero.
Hmm.
And so I guess when you are trying to learn the optimal the optimal matrix for your QUBO for your specific problem, you could restrict all the off-diagonal terms which don't exist to zero.
Yeah,
Maybe you've done that already, I don't know.
I guess one could also have this tilings be full QUBOs and with some minor embedding, but then you would have less of these tilings, right? So here from this you get 140 about, which problems that you can do then in parallel.
Yeah, I'm just wondering if somehow you could take the hardware more into consideration in your learning algorithm. That strikes me as an interesting study. Maybe you could try, if I've understood the problem correctly.
Yeah, sure, that would be interesting problem to see what what the off-diagonal elements do and how we can get more of them for the individual QUBO problems.
Any other questions from other audience members? I have another question, if that's allowed. Chairman's prerogative. So could you show the result, please? Page 32, I've noted here, where essentially your quantum annealing result is identical to your simulated annealing result, I guess. Have I understood this result correctly?
Yeah, I mean, I would guess that these are problems of lower dimension, and you take from the histogram, you take the thing that has the lowest value and okay. So, and these are here similar. Or what would you say, Max?
Yeah.
Yeah, exactly. Like here it was like trained with like exhaustive search, and then we were testing like with quantum annealing and simulated annealing, and those problems are like rather small. They were like I think like maybe like 16 by 16 or like even smaller, like maybe 8 by 8 matrices which we are solving, and then we are doing like enough anneals and simulated anneals. Then it's like highly plausible that the quantum annealing and the simulated annealing like go to the same result or like end up in the same energy. And also like this is just a histogram like over like multiple runs. So like maybe in one run we were like a bit better with quantum annealing, but then in the other better with simulated annealing. And so now it looks like the same in the histogram, but it might have not been the same for the individual solution.
So I guess from this I would conclude that there's no advantage in going quantum over the conventional simulated annealing. Have I understood that correctly?
Yeah, I would also agree for these smaller problems.
Yeah, okay.
Yeah.
So do you have a feeling for what sort of image processing problems might be more advantageous for a quantum annealer?
I mean, yeah, usually 4 key points are not that interesting, I would say. So that one would have to go up, but the limiting factor was that I think right now is that it takes a long time to train everything.
Yeah. Yeah, okay. I think Viv now does have her hand officially up. Am I right, Viv?
You are right. So yes, so the discussion of small problems suggested to ask the question about scaling up, because I agree for small problems it's very hard to distinguish performance, never mind, but on the other hand, if you are trying to scale up, where do you run into barriers first? Is it going to be on the size of the quantum annealing hardware? Is it going to be on the training time? Or is it going to be on some, or would you just choose some other way to scale up? What are the prospects for, if you like, getting to a larger size where it might be more significant?
Yeah, I think it would be training time. How would it be for this rotation estimation where we don't train, Max?
Yeah, here was like the limiting factor why I couldn't scale up more the classical hardware, because like we were using here exhaustive search, and this was just taking a lot of memory and a lot of computation time to do exhaustive search on like the bigger matrices, and this was like my main limiting factor. And when I tried like 1 or 2 runs with D-Wave, the main scaling factor there was basically that the D-Wave was too slow, like the API calls and the minor embeddings, like not the actual annealing, but all of the computational overhead we have at the moment, because we are using like a cloud service. That was there the main limiting factor.
So could you extrapolate beyond that and say, if you didn't have the access slow down, like if that limiting factor wasn't there, if you could make that fast enough, would that completely change what you were finding? Would you have a possibility to scale it up? So yeah, not taking as given the classical computer being as slow as it was, if you like.
I mean, yeah, probably it would help, but I'm uncertain, I would say, if this was the main factor.
Mm-hmm. I'm wondering what tests you could do to, if you like, separate out the effects of the different pieces. But yeah, so you have nice results, but where next? What's the most promising thing for the quantum annealer application then? And this is almost the same question as Paul asked, but a little bit different focus on it, if you like. What would your wish list be? You know, if you wanted to change something about how you are doing this, what would be the thing you would like to try next, or have barrier you'd like to have removed?
That's a good question. So one could use some larger networks, and also interesting would be, yeah, slowly changing from this diagonal baseline to something with more off-diagonal elements, and then have a look at how good this accuracy changes.
Mm-hmm. Okay.
That
Cool.
would probably be the one thing I'm most interested.
Cool. Thank you.
Kathy, you have a question.
Yeah, hi. It's actually Paul's, I apologize, I arrived late and missed the beginning of the talk, but I'll catch up. But Paul's question actually, if I understand it correctly, this is a problem that you're applying to the, without minor embedding, to the hardware as configured and seeing how well it works. And which makes me wonder if you might be interested in trying it on the Zephyr topology, which is the next one coming up. And there's a Zephyr system online. It's small, it's only got 500 qubits, but it's has 20 couplers per qubit rather than just 15, which makes me wonder if actually the other question, what's next, it makes me think that maybe that might be really interesting, just to see if the more connected topology is going to give you better results.
Yeah, that definitely sounds cool. So yeah, we only tried Pegasus.
Any other questions for Marcel and or Maximilian? Okay, if not, let's thank Marcel and Maximilian once again for a very interesting seminar. And remind you that next week's seminar is Tammy Malbash. So I look forward to seeing you all then. Thank you very much. Bye-bye, everyone.
Bye.